All right, welcome to another exciting episode here at Spain Park High School. This is Advanced Level Chemistry. Today is Friday, January the 17th. Is that right? The 17th. All right, and so today we're going to continue our talk about intermolecular forces. So intermolecular forces, what does the prefix inter mean? Say that again. Between. And so if it's intermolecular, it's between what?
Molecules.
Molecules. And what's the only type of substance that forms molecules? Covalent molecular. Ionic compounds don't form molecules. Metallic substances don't form molecules. Covalent network do not form molecules. So this only is applying to covalent molecular. What type of elements make up covalent molecular?
The 5.
No, that's
Oh, that's
covalent network.
lower.
What type of elements make up covalent molecular?
Non-metals.
2 nonmetals, right? Okay, so we talked yesterday about the first type of intermolecular force, which is what? I heard somebody say it softly. London dispersion forces. Okay, and remember those work by if I have a CH4 with a symmetrical electron cloud, a CH4 with a symmetrical electron cloud, okay? It is nonpolar. There are no poles. There's no positive or negative areas on this. But when they interact with one another, this comes this way, and they start bumping into each other, the electron clouds are negative. So what happens to their electron cloud?
They repel.
It shifts, right? It distorts. So now we have an asymmetrical distribution of electrons. Now there's more electrons over here, so this has a negative and this has a this has a positive, this has a positive, and this side has a negative. Okay? We've induced a dipole. What does that mean? Induced a dipole.
Started one.
Started one, made it happen. It doesn't happen naturally. We made it happen. So we induced the dipole. Now it has a positive and negative end. Now these aren't going to attract, they're going to repel. But you got a bazillion of these. So you have another molecule, another CH4. Let me just draw it super fast. CH4. And its electron cloud is all distorted over here because it bumped into something. So we got something positive and a negative here. So now this positive and this negative are going to attract one another. That is my LDF, my London dispersion force. The attraction between this positive of this one and this negative of this one. But after they bounce off, what's going to happen to that electron cloud? Is it going to stay distorted? No, it's going to go back to normal. So this is only, it's an induced dipole, so it's not permanent. It's only going to stay, and sometimes it's called an instantaneous dipole because it only stays for an instant. Once they bounce together and bounce back, then it goes back to normal. Then it bumps into something else and distorts the other way. And so it's constantly changing, and that electron cloud is just going from here to there, to there, to there, to there, to there. So the positive and negative portion is constantly changing, and so the attraction is only for an instant, so it ends up being very weak. All right? So all molecules exert this, but it's the only attractive force between nonpolar molecules. What did we determine yesterday, though? What is it, the strength of that going to be dependent upon? What determines the strength of the LDF?
The size of the electron cloud.
The size of the electron cloud, which we measure with the molar mass. Bigger the molar mass, bigger electron cloud. Remember I told you about the blob. The bigger it gets, the more it can distort. So if I have some huge electron cloud, you know, with the nucleus in the center, and then it goes and distorts. So now it distorts, you know, like this. Now there's a whole lot more electrons all over here on this side if it's a big electron cloud. So that makes this negative way more distinct. So it's going to be a stronger negative and a stronger positive side. So you're going to have stronger LDFs. Okay? So two things you need to take away from this. so far for LDS, okay? This is everything that we talked about, and this is all what's on here, okay? Number one, it's the only attractive force between nonpolar molecules. That's in your notes, so you might want to have your notes out too. It's the only attractive force between nonpolar molecules, and it gets stronger. The technical is with the size of the electron cloud, but the bigger the molar mass. Okay? The bigger the molar mass. And the noble gases, they act just like a molecule, even though they're single atoms. But the bigger it is, these only have, they're nonpolar, they're only going to have LDFs. The bigger it is, the higher the boiling point. The bigger it is, the higher the boiling point.
Do you have an example of a London dispersion force? Like an atom, we can like think about differently instead of looking at like the board.
All I can think of is, I mean, I'm just trying to, that's why I'm trying to give you the blob. Just, I mean, it's just, if you have this, you know, just think of like a beanbag, you know, like a beanbag chair or something. Is you know, before somebody sits in it, it's nice and round, but then when you sit on one side of it, it's gonna push all the beans to one side, and then not very many beans on the other side. And so the side where there's all the beans is gonna be the negative side, where there's not, it's gonna be the positive side. It's just gonna smush. But now you go sit on the other side, you can smush it back the other way. And so this electron cloud can constantly be distorted and changed to where the electrons aren't evenly distributed. And it's gonna cause there to be positive and negative regions in that electron cloud. So it's inducing a dipole, inducing it to be polar, inducing it to have a positive and negative end. That's the best I got.
That was that.
All right. So that's the first type of intermolecular force. London forces, all molecules have it. It's the only attractive force between nonpolar molecules. So nonpolar, and how does the strength, you know, how does the strength of, and based upon that second page, you know, what are London forces strong or weak?
Weak.
Are they just weak, or are they the weakest?
Weakest.
The weakest. Very weak. Okay? And so small nonpolar only have weak London forces, so they're the ones that are all going to be gases at room temperature. So anything, oxygen, O2, small nonpolar molecule, it's a gas. Okay? Nitrogen, small nonpolar molecule, it's a gas. Carbon dioxide, small nonpolar molecule, it's a gas. So anything that you can pretty much think about that's going to be a gas, methane, the stuff, methane and ethane that come out of here, they're small nonpolar molecules, that's why they're a gas. They only have the very weak London forces trying to hold them together, so you have to cool them down a whole lot before they'll ever be able to stick together. Now, so that's kind of goes here. So I think we already did 17. Didn't we already answer that one, make sure? Okay, because this statement here, does this statement with the previous one where we said the higher the molar mass, the higher the boiling point?
Yes.
Does this agree with that?
Yes.
Yes. Okay, now, let's start here then. According to the graph at the right, I'm gonna make the graph a little bit bigger so we can read it. In which substance, SN4H4 or CH4? So here's CH4, here's your SNH4. Which one's got the higher, they're stronger intermolecular forces?
SNH.
And how do you know from the graph?
It's got a higher boiling point.
Higher boiling point. Higher boiling point always means stronger intermolecular force. Higher boiling point always means stronger intermolecular forces. So how can you tell? Higher boiling point. Explain based on what you have learned so far why your choice should have stronger intermolecular forces. So why would SNH4 have stronger intermolecular forces, and specifically which intermolecular force? Which intermolecular force are these both got, the only ones they're going to have? LDFs, because they're both nonpolar. No phone call in it at all. Okay? So why is SNH4 stronger? Why does it have the higher boiling point?
It's bigger.
bigger molecular mass, and technically, Jacob, what?
Uh,
Bigger molecular mass is really gonna mean it's gonna have a bigger
electron
electron cloud. The bigger the electron cloud, the more polarizable it becomes, the more distortable it becomes. Okay, little tiny can only distort a little bit. A big one, you can really smush over a lot. The more you can smush it over, that's a real scientific term. The more you can smush it over, okay, then the stronger the London force. The fancy term for it, the more polarizable it is. You can make it more polar. All right, so we're looking at that. Okay, so there's there. Now, I want to keep on the graph here, but the bottom line in graph 1 shows one trend, and the top line shows a very different trend. Okay, so now all of a sudden we got these anomalies. We got this. So we got to figure this out. Now, this activity doesn't kind of go through all three. So now I want to define the other two types of attractive forces, and then we're going to come back and try to apply that knowledge to the rest of these questions. We just got this in the back side, okay? So you have your notes out now. Let's go along with the notes. Okay, so the second type of IMF is called dipole-dipole. And it is pronounced dipole. I know that phonetically it should be dipole. Okay, because the I is between two consonants, that means it should be a short sounding I, not a long sounding I, but we're saying dipole, di meaning the prefix meaning two poles. A polar molecule. This is in the definitions right there in front of you. Somebody read it for me. Who will read the Go ahead, Hilton.
The attraction between the oppositely charged portions of two or more polar molecules.
Okay, between what type of molecules?
Polar.
Polar. Dipole, that means polar, two poles. Polar attracted to polar, okay? So this is the attraction between polar. So non-polar molecules will not have dipole-dipole attractions, okay? So this is where we have HCl. Okay, now why is HCl polar? Okay, because foam call, but what again, that's true, it's got chlorine, but what is that, why is chlorine in foam call, what does that mean? Man, what were you gonna say? It is asymmetrical, okay, because it's this and this.
It's more electronegative,
What is?
the chlorine.
The chlorine is more electronegative, so we look on the table, it's 2.18 versus 3.16. So what does that mean? Electronegativity, what is that? Keep going over it, and I'm trying to get into your head. If I say, there's a rule that says you gotta say it 7 times before it finally sinks in.
Cl has more Coulombic attraction.
It's not Coulombic, well, kind of positive to negative here, but we can say it simpler. What is the fact that it's 3.16 versus 2.18? What does that mean about that pair of electrons?
Shared unevenly.
It's shared unevenly. It's the attraction, it's the tug of war for that pair of electrons. This is a measure of the strength for the tug of war for that electron. And it's a scale from 0 to 4, so that's a significant difference on a scale from 0 to 4. Okay? So chlorine's got a much greater attraction for the shared pair of electrons than hydrogen does. Doesn't have enough to completely pull it away to make it ionic, transfer it, but it's an uneven sharing. So when I look at that electron cloud, it's not going to be symmetrical like the CH4 was. It's going to be way distorted here like this. So we have what's called a permanent dipole now. It's not like CH4 where it smushes over and then goes back. It's always like this. So we have a permanent negative side and a permanent positive side. And again, this is the delta. That simply means that it's a partial positive. The electron's not completely transferred, it's just unevenly shared. If it's transferred, we just say positive and negative for an ion. But this is just not even. So another HCl doing the same thing. So this chlorine is again, pulling the electrons over there. So now I have a positive and a negative end on this one. So now, there's going to be an attraction there. This is my dipole-dipole attraction. The attraction of positive end of one polar molecule to the negative end of another polar molecule. This electronegativity is a measure of how much they pull on those electrons. The bigger this difference is, the more polar it is. You know, in your refrigerator, you got magnets, right? And some of them are way stronger than other ones. Some, you know, you can hold the good pictures on there, but some are really weak and they just kind of slide down the fridge. They both have a north and a south pole. They both are magnets, okay? But one magnet's stronger than the other. Polar molecules are going to be the same way. We can have positive and negative, but the bigger the difference between these two things, the more unevenly shared it is, the more polar it is, so the stronger that dipole-dipole attraction is going to be. Okay, here's some of my information for you. Okay? There's a quantitative measure. They put a value on how polar a molecule is, and it's called the dipole moment. Moment's a physics term measuring of the force or the electrical, you know, how much they're attracting. But the dipole moment. So the bigger the dipole moment, the more polar the molecule is. Now, I will say this in foreign language, it's just trying to convert. If something ever says, you know, HCl has a measurable dipole moment, where H2 does not, that's simply meaning that HCl is polar and H2 is not. If something has a dipole moment, that means it's polar. It's a fancy word. It's just a higher level chemistry thing. Okay? So the polarity is going to vary. So if I compared HF, okay, and HF, well, I know that fluorine is the most electronegative element. So this is 3.98 versus 2.18. So when the electron cloud gets distorted, it's even more, so that's even stronger, negative and positive. So this dipole-dipole attraction here is going to be even stronger than that one, because it's going to be a stronger magnet, so to speak. There's a bigger difference. Its dipole moment is going to be greater. Does that make sense? So polar molecules is just positive to negative. That's really easy. It's permanent. So is that going to be stronger or weaker than LDFs? Stronger, because it's permanent. LDFs is just constantly changing. Okay? Now, it's still not super strong, okay? When you look back on the second page, it's a 25 versus a 10. And those are all just general values, but it's stronger. So that's the second type. So now let's look at the third type. This is the one you learned about in biology. Hydrogen bonds. Does anybody remember what a hydrogen bond? Did they define what a hydrogen bond was or anything? Okay? Now they call them hydrogen bonds, but it's really a force of attraction. So somebody, again, go ahead, Hilty, read the definition of this one.
A special type of dipole attraction where hydrogen gets trapped between two highly electronegative elements.
Okay? Two highly electronegative elements. And it goes on to say the only elements that are highly electronegative enough, and we're going to use the acronym PHONE for this one. Okay? Plus a hydrogen. PHONE plus a hydrogen. Because, I know this is going to be deep right here. If you have a hydrogen bond, what element do you think must be present? Hydrogen. Okay? Hydrogen, but it's got to be attached directly to a fluorine, oxygen, or nitrogen. So, the most common example of this is water. Here's our water molecule. We know it's bent, AX2E2. Oxygen's electronegativity is 3.16. Hydrogen's is 2.18. So the oxygen has a much greater pull for the electrons than the hydrogen does, right? Which means the electrons are getting pulled this way, and the electrons in the bond are getting pulled that way. That makes this oxygen very negative, and the hydrogen very positive. But what's unique about this is how many electrons does hydrogen have?
2.
Try again. 1.
Oops.
Hydrogen's element number 1. 1 electron. So if that 1 electron is getting pulled away, what's left for the hydrogen atom? What's the hydrogen atom composed of? 1 electron and 1 proton. So that 1 electron gets pulled away, what's left? A proton, a naked exposed proton. All other elements have core electrons around it, shielding some of that positive with the negative electrons. But when hydrogen's one electron gets pulled away, that nucleus is fully exposed, which gives it a uniquely strong positive charge here. Because there's no other negative around it now, because it's all being pulled towards the oxygen. The oxygen is so electronegative, it's pulled the electrons this way, so it's very strongly negative. So when another water molecule comes along doing the same thing, extremely negative here and extremely positive there, now we have an attraction between this very positive and this very strong negative. It's a special, much stronger dipole-dipole attraction, to where it's the positive and negative. Notice the hydrogen's trapped between the two highly electronegative elements. All right, everybody breathe. Moving next.
So hydrogen bonds are stronger?
Then dipole-dipole. Okay? But again, if we go back to the sheet, what's the number for the strength of a hydrogen bond? 40. What's the strength of a covalent bond?
400.
400. So it's strong, but it's still the strongest kindergartner on the playground, versus the adult teachers supervising. Okay? So all of these IMFs are weak compared to covalent bonds. We're going to kind of talk about that and reinforce that. Okay? All right, but I was going to tell you to breathe. We started talking about it. Everybody breathe. Everybody refocus. Everybody quit thinking about, I wonder how many likes I have on my recent post. Okay? Because this is important. A hydrogen bond is an intermolecular force. Again, what does intermolecular mean?
Between molecules.
Between molecules. This right here is a covalent bond. It is not a hydrogen bond. This is the hydrogen bond. Okay? It's the bond between the molecules. But the hydrogen has to be attached directly to the oxygen, nitrogen, or fluorine. But when you have that, you have an extremely high boiling point. Now we need to thank God for that. Water is way up here. If it weren't for hydrogen bonds, water would be way down here. Okay? Water would not be a liquid at room temperature as we know it. If it weren't for hydrogen bonds, life on Earth as we know it would not exist, because water would be a gas. If it weren't for hydrogen bonds, the water in the Pacific Ocean would change temperatures rapidly and easily, and Hawaii wouldn't have great weather. If it wasn't for hydrogen bonds, water molecules would not separate and expand when they freeze, and as a result, they wouldn't float on top of the water like ice does, because most solids sink in their liquid. But ice floats. As a result, fish and marine life can live in the north when it's super freezing cold and their lakes and streams begin to freeze over. They only freeze over at the top. If it weren't for hydrogen bonds, those lakes and streams would go solid, and no marine life would exist in the north. It's amazing how this thing that covers 3/4 of the surface of the earth has these unique characteristics special just to water. That we happen to be on this third rock from the sun that's just the right temperature to keep this liquid water right here at room temperature to be in the liquid state. It's amazing to me that it has all these unique characteristics to it, that it just happened to be. All right, so those are hydrogen bonds. So now let's come here and look at the rest of this sheet. All right. So, the bottom line, so which has the stronger intermolecular forces? H2O or H2S?
H2O.
H2O. Why? How can we tell from the graph?
Higher boiling point.
Higher boiling point's always going to be your tell. Okay? Is it polarity or mass? Because which one's heavier? Okay, again, you can just tell, look on the periodic table, 8 versus 16. It's H2O versus H2S. H2O is gonna be 2 plus 16, H2S is gonna be 8, is 2 plus 32. Okay? So, which one's heavier, H2S or H2O? H2O, so, pardon me, H2S. So that, in terms of London forces, it would be stronger. But there must be something else going on, okay? Must be something else going on. All right, so let's turn the page. Last page, let's get through this. Okay? Now, I'm gonna make this bigger, make this bigger, so we can read it more clearly. So, we see trends with other compounds. Which three compounds deviate? So which three compounds kind of deviate from the trend here?
H2O, HF, and H3.
Okay? I think it's pretty obvious that we can see that 1, 2, those three compounds deviate, are anomalies in our graph. Right? So then it says, what are the three listed? What does that mean about their attractive forces? Are they stronger or weaker?
Stronger.
They're stronger, right? So which other elements? What are the key elements here? Okay? So when you fill in here, fill in this blank, well, both of these blanks say this basically the same thing. What's it gonna be? Okay, and I use the acronym again, phone. We got phone call and phone, and however you want it, the order doesn't matter, however you want to remember it, okay? But it's those three elements, and the hydrogen has to be attached to it, and those are called hydrogen bonds. They skipped right over dipole-dipole in this activity and went straight to the hydrogen bonds, okay? Because it's so unique. So you can kind of see, these have especially high melting and boiling points because of the ability to form hydrogen bonds with other molecules. Okay? So, because it says, so C and D say the same exact thing. Now, are hydrogen bonds, put a star by this, if you have highlighters, highlight this. Are hydrogen bonds the same as covalent bonds between hydrogen and another element? So what's the difference? What's the difference? Hydrogen bonds are what type of attraction?
Positive and negative.
Okay, I know, but it falls into what category of attractions? Intermolecular forces, meaning what? Hydrogen bonds
Between
are between molecules. What are covalent bonds between?
Between elements.
And the smallest part of an element is atoms. It's a bond between atoms. Okay? So, a covalent bond, come over here, Michael. A covalent bond is a bond between atoms. A hydrogen bond is a bond between molecules. Which one's stronger?
Covalent.
Covalent bond is way stronger.
Covalent's
40, 400. Now again, those are very approximate values, but it's giving us an idea, just ballpark ideas. Okay? Ballpark ideas, 40 versus 400. So if I take water molecules, if this is my covalent bond between the hydrogen and the oxygen, this is 400 holding this together, and this is 40 holding this together, molecule to molecule. I begin heating it up, I put water on the stove. Which bond is going to break first? 40 or 400?
40.
40. You are the weakest link. 40 is going to break. Okay? I mean, it's even like this, because if I want to try and get this off, I got to dig my fingernail in there. I mean, and this is really in there hard, and I got to put a lot of energy to break this hydrogen from the oxygen. But it's relatively easy to break the water molecules apart. Okay? So when you boil water, are you decomposing the water into the hydrogen and the oxygen, or are we just breaking molecules apart? Breaking molecules apart. Okay? So let's just finish up the last few questions and then. So what did we say? Are hydrogen bonds stronger than covalent bonds? No. So then what do you write? What's the main difference between hydrogen bond and covalent bond containing hydrogen? Between molecules, whereas the covalent bond is between atoms.
So like, with the intermolecular forces, how they like bounce off each other, is it different for hydrogen unless you're trying to boil it?
No.
So they all bounce off each other?
They do, but again, it's like bouncing off two things, like maybe two marbles bouncing off versus two things with Velcro on them.
Okay.
Okay, so if they have Velcro on them, they're gonna tend to stick together, even when they hit, they're gonna stick together. Now, if you pull them apart with enough force, they'll still come apart, but they're gonna be more attracted to one another. So and that's why, 1, 2, 1. So when we're talking about boiling points and even condensation, let's say they're all gases, and you begin cooling them down. So they're bouncing offward. They have enough energy where the attractive forces can't make them stick, but to begin to slow them down, the ones that are attracted to each other the most, they're the ones that are gonna stick together first. So they'll condense, like water will condense at 100 degrees. So now they're going too slow, now the attractive forces can take over, so they stick together and become a liquid. Whereas something like oxygen, okay, well, they don't have hardly any attraction, so you get below 100 degrees Celsius, 50 degrees, yes, they're still bouncing off. You gotta get all the way down to almost negative 200 degrees. So somebody get down to negative 200 degrees, okay? And then finally, they'll stick together if you get them going slow enough. Helium, you have to get them almost completely stopped because it's the smallest. It only has London forces. It's only got the tiniest little, only 2 electrons in an electron cloud, so it doesn't distort hardly at all. And so you got to get it down to 4 Kelvin, get them almost completely stopped before they'll even think about sticking together. Does that make sense?
Yes.
Okay, so they're always bouncing. It's just however more strongly they're attracted to one another, you have to put more energy to get them to break apart and stay apart. And that's what the boiling point measures, is that strength of attractive forces. The more strongly they're attracted, the higher the boiling point, the more energy it takes to break them apart, and you got to keep them moving in order to, to keep them staying apart. All right, so what I just gave to you is the entire chapter 6 in review. This is the entire, all your 12 pages of notes summarized right here. Okay? We have 4 types of substances, so everything that we're going to go through, and all the properties that we look at, you have 4 types of substances. Ionic, metallic, covalent network, covalent molecular. How do we know if something's ionic? It's a metal and a non-metal. Okay? And then metals, ionic compounds, this is deep again. Ionic compounds are composed of what?
Ions.
Ions, not molecules. Ions. So what holds them together? What's the bond?
Ionic.
Ionic, but the ionic bond is the electrostatic attraction from transfer of electrons. So you get, that's the positive to negative attraction. That's this, okay? Positive to negative. Okay, electrostatic attraction. And what's another name for an electrostatic attraction? Coulombic attraction. So if you want to write in there, Coulombic attraction on that, okay? We know why they're brittle. You change it, positive gets next to positive, negative gets next to negative, okay? They don't conduct in the solid. What's electricity? The flow of charged particles. You got charged particles, ions here. Why can't this conduct as a solid?
Because it's a crystalline structure.
Meaning? Electricity is what again? The flow of charged particles, and here and there. What you just say, Ryan? They can't float. They can't float. So how do you make them, how do you give them the ability to float?
Heat 'em up or speed 'em up.
Heat them up, melt them, or put them in water, dissociate them, to where then the ions are free to move, then you conduct. Okay? An electrolyte is just a substance whose water solution conducts electricity. Okay? Most are soluble in water. When we get into chapter 13 to talk about solutions, we'll talk about more of these attractive forces and why they're soluble. Okay? And they have super high melting points. What does that mean about the strength of the ionic bond? It's very strong. Higher the melting point, the stronger the attraction. But it's not an IMF with an ionic compound. It's an electrostatic. It's Coulombic attraction in an ionic compound. And then we have metals. How do we recognize it's a metal? It's only bonded to its own self. Gold bonded to gold bonded to gold, copper bonded to copper. And the answer to everything metallic is the sea of free-floating valence electrons. So we have charged particles that can flow. They don't dissolve, so they're non-electrolytes. Okay, they're malleable and they're ductile. Okay, all the different things there. How do we know if it's covalent network?
One of the 5.
It's one of the 5. What are the 5? If I were you, I'd write the 5 right into there. What are the 5? Diamonds, graphite. And those are both forms of pure what? Carbon. Diamonds and graphite. What else? That's pure carbon. Pure silicon. Notice again, they're in the same family, carbon and silicon. What's the 4th one? Silicon dioxide, which is sand, SiO2. So diamonds and graphite, pure carbon, pure silicon, silicon dioxide, SiO2, sand or quartz, and then the 5th one, silicon carbide, okay, SiC. SiC. All right, and they have all those, so they're held together by covalent bonds. Again, they don't form molecules. So the carbon atoms in the diamond are held together by covalent bonds. Are those strong or weak? Are covalent bonds strong or weak?
Strong.
Strong. So they're going to have high melting points again because you have to break the strong bonds holding them together. They're very brittle. Okay, all the different characteristics. Just think about a diamond when you want covalent network. You know, it's brittle, it's not soluble in water, high melting point, okay? And then we get to covalent molecular, and there's 2 categories. Both of these are covalent molecular, just nonpolar and polar. So we have to be able to identify then, is it polar or nonpolar? We had our rules for polarity on the board, okay? If it's nonpolar, we only have London forces. Are those strong or weak? Super weak. As a result, they have low melting points. They're generally gases. If it's a big molecule, maybe it's going to be a liquid, but it's going to be a volatile liquid. And what does that word mean, volatile liquid? Easily evaporated, because even though they're, the bonds still aren't very strong. They're still going to evaporate. Gasoline, acetone, fingernail polish remover, paint thinner, all of those things evaporate real quickly, because they're, even though they're liquids, they're bigger molecules, but they still have those weaker attractive forces. Okay? And then if it's polar, then we have to look, okay, it's automatically going to have dipole-dipole. It's got London and dipole-dipole. But then, so I would write out here, I would put out here, this is phone call. Whereas this is which ones? Hydrogen bonding. So it's hydrogen plus foam. Okay. Now this is here, like dissolves like. This was the styrofoam cup demonstration I did for you. Okay. The styrofoam is non-polar, so it did not dissolve in the polar water. It was insoluble, so styrofoam cup's great to do anything that's water-based. But as soon as I put the acetone in it, okay, like dissolves like, I put the non-polar into it with the non-polar. Now, sugar you guys remember that sugar's got a whole bunch of OH groups on it? So what does that mean sugar can form? It's got OH. Can form hydrogen bonds. Water can form hydrogen bonds. So as a result, sugar is very soluble in water. The water and the sugar hydrogen bond with each other. You know, it's got all kinds of places for the water to attach to it and pull it into solution, and so it's very, very soluble. So life dissolves like. So everything that we need to know about the molecules, this is the chapter 6 in review right here. So you can kind of use this kind of as a guide as to knowing. But these are all the steps and the processes we have to go through. Okay? And that's what makes it hard, is because you know, if I want to know, well, let's even look at this. We go and we look at this worksheet now. All the things. We have to know how to draw our Lewis dot structure. So we've drawn the Lewis dot structure. You already have this. We've drawn the Lewis dot structure. We know the shape AX5, so we have to understand how to bond. We have to draw the Lewis dot structure. The Lewis dot structure tells us what the shape's going to be. And based on the shape and the types of bonding, we can tell whether or not it's polar or nonpolar. Why is this one nonpolar? It's got phone call in it. It is an expanded octet, but it could still be polar. It's symmetrical. And how do we know it's symmetrical? Because all of the bonding atoms are the same. Trigonal bipyramidal is a symmetrical shape. Most of our asymmetrical shapes have a lone pair on the central atom, at least one. Now that's where we had the two exceptions. We have the two exceptions right here. We talked about that. But most of the time you can just kind of look. But if all the bonding atoms are the same and there's no lone pair, it's symmetrical. So it's nonpolar. So what's the only type of IMF on this? What's the only type of IMF? London dispersion, LDF. Okay? So I'd go ahead and write that in the corner. CO2. Why is this one nonpolar? It's symmetrical again. Linear is symmetrical. So what's the only type of IMF? LDFs. But water is bent. It's polar. So what type of IMFs does it have? It's got hydrogen bonds, but it always says LDFs. Okay? And it's polar, so it's going to have dipole-dipole. If it has hydrogen bonds, it has all three. Which is why water's boiling point is so high for a small molecule like it. Okay? But PCl3 is polar, so it's got London and dipole-dipole, but does it have hydrogen bonds? No, it doesn't have hydrogen, and it doesn't have fluorine, oxygen, nitrogen. Okay? Tuesday, if we're here, we're going to do a lab on all this. Okay? Wednesday's mock ACE AT. Thursday will be a review. Friday, ideally, would be a test. And does anybody understand this T-shirt?
I actually tried to figure it out, but I have no idea.
Good? Hobbs?
Well, we can.
Get the
Okay.
joke.
What is 1, 0 in binary the number of?
Oh.
No. 1, 0 in binary is what number? Nobody does this, and nobody's in engineering or coding? It's 2. So there's only 10 types of people that understand binary. Okay? That's binary for 2. There's only 2 types of people that understand binary. All right. Y'all have a wonderful weekend and go Jags.